Hey, how you doing? My name's Elton. Welcome to Learn Docker in a Month of Lunches. So this is episode 15 of the series. Today we're looking at multi-architecture images, which is how you can package up your application so that it runs in containers across different platforms. So it can run on Linux or Windows, Intel or ARM. And the reason that fits into this week when we're all learning about orchestration is because you can have a cluster that has a mixture of different platforms. So I can have a single cluster with some Windows nodes and some Linux nodes, some Intel and some ARM. That's true of Docker Swarm and of Kubernetes. So you can have this kind of hybrid cluster that lets you run all your workloads. Because the point of this is your application modeling, the way you model your application in your Docker Swarm YAML file or your Kubernetes YAML file, is the same pretty much, apart from a little flag you put in to say whether this is ARM or Windows. So you have a single application modeling language to run all your containerized applications, whether it's a 15-year-old Windows application or a brand new Go application. So today we're going to learn about multi-architecture images. So let's swip over to the slides. Okay, and for those who are new to the series, so it's always the same format. I spent a couple of minutes going through the website for the book, which kind of gives you all the links to everything that you want to see to find out what I've been doing in the series and the other episodes you might want to watch. Today is all about chapter 16 of the book, which is building Docker images that run anywhere: Linux, Windows, Intel, and ARM. And then at the end there'll be a little Q&A. I forgot to say yesterday, but I'm running. If you're watching live, I'm running slightly earlier than usual. So if my usual people are going to join late, then you might miss the Q&A. But if there's any YouTube comments, if there's anything in Slack, then I'll pick that up and we can talk about that at the end. Okay, cool. So let's get on with the show. So if I switch to here and go over to my web browser. So this is diamol.net. This is the homepage for the book. This is where you're going to find all the links to the Slack channel, to buy the book from Amazon or Manning, and to get all the source code on GitHub. So if you don't want to buy the book, that's totally cool. You can still follow along with all the exercises, all the Docker files and everything. They're all up on GitHub. The Slack channel link is here. This is the link to the latest stream, and that's the link to the giveaway. I have a giveaway every week while I'm doing it live, and I often have stuff to give away. So check that link, even if you're watching like on demand later on. Kubernetes is the sequel. So after this book, the Kubernetes book is one you should bookmark. And then here's the list of episodes. So they're broken roughly into 4 weeks with 5 episodes each. And each episode kind of has a tightly focused topic. It's a very hands-on way of learning Docker. So you do lots of exercises. You get lots of experience using the Docker command lines and the Docker syntax for Docker files and everything. And then each of those 5 episodes is kind of built into an overall theme. And this week, we're looking at running at scale, and we're just finishing this week off. Okay, so let's go and check out the book. So this is the chapter 16. It starts with the kind of disclaimer, because if you've been following along so far, at the start of the book, I point out you can use any machine that can run Docker to follow the exercises in this book. And without going into too much detail, because to go into that much detail early on would kind of bog you down in a lot of stuff that you don't need to care about. So it's not until this point that I'm asking you to think about, like, how does that work? How can I run the same Docker command on my Windows container on a Windows server machine in Azure, and also run the same command on my Raspberry Pi and get the same output? Well, today is how you find out. So it's all about multi-architecture images. So the idea is that Docker knows, when it packages the image up, what architecture it runs on, what architecture is built to support. And that means the operating system and the CPU architecture, the combination of those things dictate the type of machine that image can run on. And here we're going to learn about like how that works and how you can package your image to effectively have different variants of the image for each of those individual operating systems. And so that when you do your Docker run command, Docker pulls down the right one depending on which platform you're using. Okay, and if you've got this far and you're about to switch off, this is why you should care. So Amazon Web Services, so AWS, you can go and spin up a virtual machine that's running on an ARM processor. If you're not familiar with ARM, like ARM is the silicon that's inside every smartphone, every tablet, everywhere. It's a different instruction set from the standard Intel and AMD processor that you've probably got on your laptop or your desktop or your server. And ARM is a much more lightweight architecture. So what that basically means is that the chips run more efficiently. So you might not care about that in your desktop. If you're a climate denier, you might not care about that anyway. But in a data center environment, power becomes crucial. Power is cost. So what Amazon have done is they've spun up the availability of a whole bunch of ARM virtual machines that run on physical ARM chips inside their data center. They're a lot cheaper for them to run, and they pass that cost saving on to you. So ARM machines in the cloud in AWS are very nearly half the price of the equivalent Intel machine, and they run a comparable performance level for most types of workloads that you're probably going to run in containers, like web applications and APIs and batch jobs and stuff. For most of those workloads, an ARM CPU is fine. So if you're about to think, I'm not interested in this multi-architecture stuff, if you don't use Windows, that's fine. But the ARM bit should be the killer, because you can be the person who goes into work on Monday and says, that cloud build that we're worrying how to get down, we can almost cut it in half if we just rebuild our images and publish into AWS and use ARM CPUs. So that's why you should care. Okay. And incidentally, this is not a niche user case. You can spin up a Kubernetes cluster in AWS, and you can have some Windows nodes, some Linux nodes, and some ARM nodes all in the same cluster. So this is not something that you have to kind of tweak a bunch of weird settings to do. You can just do it with EKS which is the command line to spin that stuff up. Okay, and then IoT devices. So IoT is becoming more and more popular. It's a really difficult problem to solve, is how to get software out to a device that is only on occasionally, has tiny bandwidth, and containers are playing a big part in that. Okay, but we're going to kick on with the demos here. So this is for this to work. The exercise is at the start of this chapter. You need Docker Desktop. So what I'm going to do is I'm going to build on my Intel machine. I'm going to build a Docker image which targets an ARM CPU. Now it's physically a separate CPU instruction set. So I can only do that with emulation, and Docker Desktop has emulation built in to do that for me. So if you're running Docker Desktop, let me open my dashboard, which I've got over here. So Mac or Windows is fine, and you need to be in Linux container mode if you're on Windows. Open up the settings, and under Docker Engine, make sure you've got this experimental flag. So the experimental flag is what Docker introduced for new features that they're kind of, it doesn't mean they're poor quality. It just means that the API might change and the way it works might change. So don't bank on this for production use. The emulation that I'm going to show you can use that to get started and see how this stuff works. In reality, you want to build on the actual architecture and then push your images from, if it's an ARM machine, build it on ARM. But this is a good way to get started. So I'm going to take that. I'm going to make sure that experimental setting is enabled. And now I'm going to go and run my exercises. So let's see where I am in here. I'm in the DIAMOL repo. So all this stuff, this is the repo that is up on GitHub. That's on the link from the website. So I'm going to switch to the right directory. And I'm going to build an image here from the Who Am I directory. And I'm going to have this platform flag. So this is stuff you've all seen before. Docker build is an alias for Docker image build. -T is the tag that I'm giving it. I'm using Linux ARM64 as the image tag, but I don't have to do that. It's just to help me work out what's what. And this platform flag is the thing that in Docker Desktop will apply the emulation. So when this runs, it will run inside an emulator that is pretending to be Linux running on an ARM processor. Okay, so I've already built all this stuff before. So have I built this before? Depends how long it takes. If it takes a little while to run, then obviously I haven't built it before. So the thing about emulation is, and the reason why this is just to kind of get an idea how this stuff works, is that emulation is pretty slow. So you'll see that this is at this stage in the build, this is a multi-stage Dockerfile. It's a .NET Core application, which is cross-platform anyway. So the prerequisite to having this work is that the application that you're running, the application platform itself, needs to be cross-platform. So like Go, .NET Core, Java, Node.js, all those things have ARM and Windows equivalents. So that's all fine. So it's running in my emulator. So there's two problems with that. Firstly, it's slow. And secondly, you get these kind of unknown errors every now and then, which may or may not be important. Now, I happen to know for this little application, these errors that come through don't make any difference. So I'm just going to let this run through, and it'll take a little while. But for the images that I actually publish for the book, so all the images that I pre-build, so every time you do a DIAMOL image, which is Postgres or a chapter of one of the demos for the chapter, I've got actual ARM machines lying around my office. And I have Jenkins builds that kick off a build on a Windows machine, a build on a Linux Intel machine, and a build on my ARM machines, and then push them all up. So I don't have to deal with the emulation. But this is going to get you kind of looking to see how this stuff kind of works. And we're going to inspect this image in a second. And we'll see that it is built for Linux operating system, ARM64 architecture. And so on a real Raspberry Pi machine, on a Raspberry Pi 4 or above, that is the genuine 64-bit machine, you can install Docker. You can do a Docker run of this image name that you've built and pull that down from Docker Hub, and it will just work. So the emulation is kind of good enough to get this up and running. It's still taking a little while to build there, but I think we're getting there. So this is the compilation. So the thing about emulation is it kind of shows you the bits of your build that are expensive. So compiling a program is typically quite an expensive thing, but that's done now. Okay, so I get my usual security warning because I'm running on Windows. And now if I run this, as long as my setup is correct, if I inspect that image, so I'm doing Docker image inspect, standard inspect command, I would get a whole chunk of JSON out, but I've got a format flag in here to say the only things I'm interested in are the operating system and architecture, and the output I get is Linux ARM64. So I've built it on a Linux Intel machine, but I get the image itself is good for Linux and ARM. And if I go and do a Docker info of my actual machine, I can confirm that I'm using x64. So that's AMD Intel 64-bit chip. So it's how I can kind of build this up and get up and running and see how this works. So you can you can try your application and just see what it looks like in an ARM environment. Okay, so this is the bit about the Dockerfile here. The Dockerfile is using images that already have multi-architecture variants. So if I open that Dockerfile, we're in 16. Who am I? Here's the Dockerfile here. It's a standard kind of multi-stage Docker file. The from line uses an SDK to do the compilation. And then in the final application image, we've got a runtime now, which is ASP.NET. They're both multi-architecture images. So the only way this works is that when I have the platform flag, I'm saying to Docker, you pretend that you are an ARM machine, even though you're Intel. So when it does the pull to get the image for the SDK, it will pull the ARM version. And similarly, for when it packages it up, into the final application image, it will pull the ARM variant of that image. So those from images need to be multi-arc if you want to do a multi-arc image yourself. Okay, so that's the first demo. So I could push that to Docker Hub. I could run it on a Raspberry Pi or an A1 instance on an AWS, which are the ARM instances, and it will just run natively. So I've built it on a completely different CPU, but that's something that I can use with the same Docker run commands. Okay, so let's scroll on down here. So Docker knows all this stuff. So when you try and pull an image, Docker knows the architecture that you're using and the architecture of the image that you're trying to build, that you're trying to run. But it doesn't stop you pulling something. You have to run the image command. You have to run the image pull command first to see whether that image is suitable for your application, for your engine. So I'm running Linux here. So if I do a Docker version command, that will show me the version of my engine, which is Linux, AMD 64. If I do a Docker image pull and try and pull a Windows-based image, so this is all the Windows images. Microsoft hosts them on their own Docker registry, which is mcr.microsoft.com. So they have the official images on Docker Hub. That's where all those images get kind of publicized, but you physically pull them from Microsoft's container registry. This is Nano Server, which is the trimmed down version of Windows Server. If I try and pull it on a Linux machine, it says there is no matching manifest in the manifest list entries for Linux AMD 64, which basically says I can't use this because these variants that I'm talking about, each variant is listed in the Docker Hub. When you push your image, it knows about the variants of the image that are available, and it knows that I'm running Linux AMD 64, and the only variants that are available for that particular image are Windows variants. So I can't physically run a Linux container on a Windows container on a Linux machine. Okay, so it gets that, checks from the engine that's running, finds the current architecture, sees if there's a match for that in the registry, and if there isn't, it doesn't get pulled. That's it. I can't run that container. Now, that's always going to be true of trying to run Windows containers on Linux because there's a whole licensing issue in there. But the reverse is a bit more blurred. So you can kind of run Linux containers on Windows. I'm doing it in Docker Desktop, but I'm not because I'm using Windows subsystem for Linux. So I've actually got a Linux kernel running inside Windows, and Docker's running on the Linux kernel. So I'm not really running Linux containers directly on the Windows kernel. There was a couple of kind of projects to make this happen. So there was this LCAR project which did emulation within Windows to run a Linux container, but that kind of went. I'm not sure that kind of went very far. But WSL, which is coming to Windows Server, is going to be how you do that. But the rule of thumb is, if you want to run a container that's built for a particular architecture, then you need to run it on the machine that is that architecture. Otherwise, there's some form of virtualization or emulation happening, and that's going to stop you getting all the performance benefits from just having a container, because they expect to run, to get all the benefits, the container runs directly on the kernel. Okay, so stick to the matching architecture, and then this is how you support that as an image publisher. You build these different variants of your image, and you push them all to your registry. And then whoever's using, whether they're using Windows or Raspberry Pi or whatever, when they do their Docker image pull or their Docker container run, Docker will pull the matching version from the registry. And there are a couple of ways that you can do that. The first way is the one that I've shown you so far. If your Dockerfile, if all the from images are multi-arc images themselves, and the instructions that you're putting in are exactly the same no matter which environment you're running in, then you just need a single Docker file. I can take this Docker file that is cross-platform itself because it doesn't do anything specific to Linux or specific to Windows. It's just using standard Docker commands, and I can build it on each of those in different environments. So here I've got my Windows machine, my Linux Intel machine, my Linux ARM, and my Linux 32-bit ARM. Same Docker file. Each of those engines will go through and build the image itself and produce a separate image that's tagged for its own architecture. So if I've got a build farm, which is what I've got in reality, and what you would look at doing if you need to support this in it for a production application, then you're gonna have different architectures, and each one will build its own copy. And then you'll push them all up to the registry along with this manifest, which we'll come to in a second. So this is the kind of nice way if your Docker file lets you be able to package things up in a different way, but you can't kind of always do that. So sometimes you have to adapt what's going on inside each Docker file for different applications. So maybe I want to use a different from image because the Windows version. Maybe there isn't an official image that I can use for the Windows variant, but there is for the Linux variants. So in that case, I'll have a Linux Docker file that uses the image from Docker Hub, the official image from Docker Hub, and my Windows Docker file will produce like effectively the same output. So the application in the image will behave in the same way, but it's built in a different way. So in that case, you need to have this approach where you have multiple Docker files tailored for each architecture. So maybe I've got a Windows Docker file. I've got a Docker file which works for Linux on Intel and ARM64, but for some reason, maybe I use a different base image for the Linux ARM 32-bit one. So the end result is the same. I've got images that are built for each architecture that I want to support, but I've got different Docker files to manage for each of them, which kind of gets a bit of an overhead that you have to manage because I'm working with like what are effectively variants of the Docker file that are trying to achieve the same thing. But it means that I can tailor what I need to do for each of the architectures that I want to support. So you've got that freedom. Docker doesn't care. So when you push these images up to Docker, it doesn't care how you built them or whether several variants are from the same image. It makes no difference to Docker, but it gives you a bit more of a management overhead. And the advantage of the management overhead is the price you pay for having the flexibility to put whatever you want inside your Docker file or whatever you need to keep those things working. So we're going to see how that looks. So inside here, let's clear this down. I'm going into this directory here, which is called folder list. I'm going to build an image which is targeted for Linux AMD 64. So this is the Intel build. There's a little table coming up that tells you what all the code names mean for all the different architectures. So we'll see that in a second. So I'm going to build that. So this is taking that one Docker file that's in there, and it's building it targeting Linux AMD 64. So there's no platform flag in there, so it'll just use the native architecture. If I build this for exactly the same, this is separate Docker file, and I build that for the platform Linux ARM 64, then I've already built these. These come from the cache. And if I build it for ARM 32-bit, there's a different Docker file again. So I'm going to build all these things, and then we're going to look at the Docker files. So let me clear this down. If I run the AMD variant, this is the Linux Intel variant, what it just prints out some stuff. So it tells me that it was built as Linux AMD 64, and it's currently running on Linux, and it's x86 64. So that's Intel 64-bit. And I've got the others coming up in here in the same way. So let's clear this down. Go and check out the other ones. So I'm using the tags in this instance to identify the different variants. So I've talked in previous episodes about how the tag becomes your version number. Well, the version number is only part of it. If you also support multiple architectures, then you'll probably include that in the tag as well. So the full tag for this, if it was a real application that I was publishing, it might be colon 1.0.1 dash Linux dash ARM64. So I've got all that information in the tag. So in this case, I've got Linux ARM64, and it's built as Linux ARM64, and then you can see it's Linux, and then ARch64 is the code name for one of the 64-bit ARM chips. And close that down, and then last of all is the 32-bit ARM, which by convention is just called ARM, and the 32-bit variants, the 64-bits are called ARM64, and this knows it was built as ARM32, and inside it's an ARM v7, so that's a 32-bit ARM processor. So using emulation, I've got what I needed. But in order to get there, I had to use a whole bunch of different Docker files. So if I open the builds here for this folder list, like all it doesn't do anything particularly clever. All it does is it starts from DIAMOL base, which is a multi-architecture image. So there are ARM 32 and 64 and Intel, Linux, and Windows variants of this already. Copies in this file, and it echoes what it was built as. This is the multi-arc version. So the Linux version starts on specifically from a tagged Intel Linux base image, and it just writes out these kind of hard-coded lines. And it's the same. It uses uname, which that's how we print out what version of the operating system it's got, and it uses ls to list out the folder contents. That's all it does. The ARM one is almost exactly the same, but it uses a different base image, and it prints out ARM32, and then it does uname again. And then the ARM64, again, same thing, different base image, different hard-coded string. The interesting one is the Windows one, because this comes from a completely different base image again. This is Windows base image, but I can't use the same instructions to get my application to work in the same way. So all this app does is it prints out the version of the operating system and prints out the file contents of a directory. But I can't use uname and ls inside a Windows container because it doesn't have those commands. So what I'm doing instead is I am switching the escape flag. So the other thing is Windows uses backslashes for file paths. So if I want to include those in my commands, then things get kind of funky. So Docker lets you switch to using a different escape character, and I'll use the backtick, which is more conventional in PowerShell in Windows. And then same thing, I create the directory. So these are all standard Dockerfile commands that work the same way no matter what architecture you're using. But as soon as I get to a command instruction, that runs inside a container and executes the command. So in this case, I've got my echo to say that it was Windows 864. And then I've got a completely different, from the uname, I'm echoing out these environment variables that Windows provides, telling me what the processor architecture and the identifier is. And then I've got the dir command instead of the ls command. So as a user, I get the same experience. The app works in the same way in my container, but it's packaged up in different ways to suit the target architecture. So this is the scenario where to get the end result, I have to package up different Docker files to get there. Okay, so let's close this down. Go back to the book here. So Docker will use emulation when necessary. So here it's emulated. It can't emulate Windows on Linux. So I can't build a Windows variant from the Linux machine, which is why all these examples use Linux containers and get you to build the ARM variants, because the emulation supports that. If you want to build Windows containers, you need to have a Windows machine, and you need to be running in Windows container mode on Docker desktop. Okay, so this is the variants are all very similar, and this is the bit that shows you the differences. So the uname bit only applies in Linux. This would fail if I tried to run that in a Windows machine. Some commands are the same. So echo kind of has the same syntax, but the uname isn't there. So I have this processor architecture environment variable, and I'll use dir instead of ls. So it's tailored to what the architecture supports. Okay, and if you try and do this as a multi-architecture with a single Docker file, then things don't work so well. So if I do the Docker image build for this other Docker file, which is the first one that we looked at, actually, that I skipped over, and we will come back to. So I'm not doing any kind of platform stuff. I'm just doing a Docker image build. So this will be a Linux Intel build, because that's what my machine is. I've already built this why it's super fast, because it all comes from the cache. And now if I try and run that, it all built correctly. So it executed all the commands inside the Docker file correctly. But now when I try and run it, I've got a failure. So the uname bit ran, but when I tried to run dir, that failed because I'm running on Linux. So what's actually happened here is I've attempted to get a kind of a multi-arch build, but what I'm doing is I've kind of got myself confused. So what I've got here is I'm using the multi-arch base image, so that's fine. So this will compile on whichever is the relevant architecture where I build my own image. The echo, that's fine. That works for Windows and Linux. Then I've got uname. That's only going to work for Linux. So if I build this on a Windows container, this will fail at runtime. And then the dir will only work on Windows. This will fail in Linux at runtime. Because it's part of the command instruction, this isn't validated in any way. The command instruction is really just metadata that lives alongside the image, so Docker knows what to do when it starts a container from that image. So in this case, it's going to run this command in the new container, and it will fail anywhere you try to run it, because I've got one Linux command and one Windows command, so it'll fail on both systems. So this is the thing you need to be aware of. If you're building Docker files, even if you don't plan to be multi-architecture from the beginning, try and build your Docker files so that you could go multi-arch. So you can support Windows users later on, or you can support ARM processors later on when you support some sort of IoT device. So if you've built your command instructions so that they assume you're running on Linux, then you're limiting the exposure of your application. You're limiting the potential runtimes for it. Okay, so those are the screenshots from when I did it in the book. Here's the all important table. So if you're not familiar with this stuff, for reasons of historical lack of interest, the Intel chipset, the x86, the 64-bit version was kind of called x86 underscore 64 because it's an evolution because 64-bit Intel can run 32-bit apps too. For reasons that we won't go into, the kind of code name for that is AMD 64. So if you've got an Intel chip or an AMD chip, 64-bit, like pretty much all the modern chips are the same chipset, AMD 64, otherwise known as x86 64. So, and when you're on Windows or Linux, it's the same CPU, different operating system. The In the ARM world, 64-bit ARM is typically known as ARM 64 as a platform flag in the Linux world, in the Docker world. The actual CPU names, there's a whole variety of different names. It may or may not. The most common ones are ARch64 and ARM V8. So those are the ones you see, but there are kind of variants of that too. And the 32-bit ARM in the Docker world, it's just called ARM because in the old days there only was 32-bit. And then all these aliases, and there are variants of these two. There's ARM 37, there's ARM V7, and there's ARM HF. So those are kind of 32-bit things. So, and that's important because if I've got a Raspberry Pi 3, that's 32-bit ARM. I can't run an ARM 64 image on there because there's not a match for the CPU instruction set, so that will fail to run. So if you want to support, these are the main four, really the big four. Um, Docker supports all those, and it supports more too. So coming down here, if you have an IBM Z, which is one of those like massive mainframe boxes, or a Power PC, like these big IBM mainframes, they run Linux. They support Docker too. So I don't include every platform that Docker supports in here, but it supports some of these bigger machines too. So if you've got mainframe stuff and you want to look at containerizing that, like you totally can. You can take your COBOL application and you can package it to running Docker containers on your IBM Z if you've got one. I don't have examples of that in the book because I'm guessing most readers won't have one. I certainly haven't got one myself. Okay, so that's only the first part of the puzzle. I can build all these different variants of the image, but just like any images that I build, they only live on the machine where I did the build until I push them and share them on Docker Hub or any other registry. The registry format, the image format, and the manifest format, which is the thing that describes the images. Again, that's an open standard. Doesn't really matter what registry you're using. So we've seen that MCR is the Microsoft Container Registry that supports multi-arch versions of its images, just like Docker Hub does, just like ordinary registry container. If you run your own registry instance, that supports multi-arch images too. So there's nothing special about Docker Hub to make this happen, but Docker Hub is the most common. So the way you support this is first of all you push all those images. So there are two options for pushing your multi-arch image. I'm going to show you the old-fashioned way first, and then later on we'll come and do the new-fashioned way. The new-fashioned way is much slicker, but it doesn't support every scenario. So you need to understand like the original approach to understand where you can and can't use the new approach. Okay, so I'm going to put my Docker ID in a variable. So I'm on Windows, so I need the dollar syntax. My Docker ID is six-side. Yours is whatever it is, your Docker Hub ID, not your email address, your actual ID that you see when you tag your images. I'm going to tag my image here. The only reason for capturing that variable is so that you type in one thing and then from here on in you just copy and paste the commands. So I'm tagging all those variants that I built earlier of that folder list image, the thing that was variants for Linux, Intel ARM, and ARM 32-bit. So I'm just tagging them with my Docker Hub ID. So that's tagged them all. So just locally with my six-side name. And now if I push them all, even though you've got different tags, if you do a Docker image push without a tag on the end, so without a colon, it will push all of the tags. So it's going to push all of my instances, all these three that I've built up here. They all already exist because I've already pushed them. So if I go and have a look at Docker Hub now, so if I go to hub.docker.com and there's my six-side user, the most recent image that I pushed should come to the top, should surface away to the top. There's my folder list updated a few seconds ago. And if I go and look at the tags, and we'll ignore the latest tag for a second, here are the ones that I've just pushed. So I've got this Linux ARM64 tag with a digest, which uniquely identifies the image. I've got my ARM, I've got my AMD64, and Docker Hub knows what they are. So the architecture is part of the image metadata. So Docker Hub knows where these things are, what these things are for, and it tells you all the different variants that I've already pushed. But those are just individual images at the moment. So I could do a Docker pull six-eyed slash colon Linux ARM, and if I'm running on an older Raspberry Pi, I would pull that image down. But what I want to do is I want to support people just using the six-eyed or the DIAMOL slash ch16 folder list without the tag. And that's where the manifest comes in. So each individual image, you push all those to Docker Hub, and then you push this thing called a manifest, which is the alias. Really, it's an alias over all those images that supports all those architectures in a single image tag. Okay, so the way we do that, for that to work, you need to be using, again, it's another experimental flag. You need to be on the experimental command line. So again, on Docker desktop, on Docker, if you're using the standard Docker engine on Linux and the standard Docker command line, there's a config.json file where you put the experimental flag in as well. On Docker desktop, it's easy. You just click that button. I've already clicked it, as you can see. And that enables the Docker manifest command. That's how you do it if you're running on Linux. This is the thing you open, and that's the value you put in. The Docker manifest command, again, it's experimental because a few things have changed over how it works. Like I'm expecting there'll be some performance updates because it's not super fast, but it does its job. So if I go into a Docker manifest inspect, what that's going to do is going to go to the registry and ask it about all the variants that it knows about for that image tag. So the tag there, diamol slash base, that's the kind of umbrella tag, the kind of the overarching tag for all the images that lie underneath. So if I inspect the image, it takes a few seconds because it goes and gets a whole bunch of data from the registry, and then it will print me out a ton of JSON telling me about all the different variants that use that same image tag. So remember, this is one image tag with lots of variants underneath it. So in this case, I've got a Windows AMD 64 variant, and that's Windows Server 2019. You can also include, as you see here, the operating system version, which is more important for Windows containers than Linux containers because backwards compatibility is not quite so free ranging in Windows containers. Up here, I've got an operating system, Linux, and ARM64. This is the digest. That's the kind of ID that you saw in Docker Hub. Further up here, I've got Linux ARM here, so that's my 32-bit ARM. And if I go all the way up, I'll see my Linux AMD 64. So below the manifest, I can see all the variants of my image, and you can see the diamol slash base image is a multi-arc image. So whenever you do a pull, I don't need to say diamol slash base colon Windows dash AMD 64. If I'm running on Windows on Intel, I would get that image because Docker will say, this is the operating system I've got, this is the architecture I've got, bring me the matching image. And the registry, if it's got it, it will download that image. If it hasn't, as we saw right at the beginning, you'll just get an error. Okay, so let's scroll down here, and now we're going to see how to do your own manifest. So there's this idea of the manifest list, and this is kind of my visual representation of it. So that's my image name, that's the tag. Underneath, that's the umbrella. And then underneath it are all these individual images, which happen to be built for different operating systems, different architectures. And then Docker does the smart work of saying, well, this is the engine architecture is this. That's the version of the image that I'm going to pull down for you. So you don't need to dig down yourself. Most of the official images on Docker Hub are multi-arc. They don't always have Windows variants, but a lot of them do now. So you can just use the official image name and the official image name with the version in the tag without having to worry about the actual architecture. Okay, and then for our own application, what we're going to do is we're going to run this command, docker manifest create. And the manifest is this list of all the variants that you support in your multi-architecture image. So all the manifest create command syntax, it just takes a big list of all the image variants that you support. So these are all the images that I've built. That's the Intel Linux one, AMD 64, ARM 64. Sorry, this is the umbrella name. And then after that is all the variants that you support. So I'm probably getting an error with this because I've already run this command. So let's just see. Yeah, it refuses to do it because I didn't specify the amend flag, but that's okay because I've already created my manifest. That lives locally until I do a push. So manifests live in the registry, and they group together a bunch of images that also live in the registry. So I do my Docker manifest push. It's going to push that umbrella list up to Docker Hub. I get the same thing out. I get some sort of unique ID back out. And if I flip back over to Docker Hub and do my refresh, I'll see here when it loads up, I'll see my latest tag, which is the one that I've just updated here. This is my latest tag, which has all these digests with all these different architectures in them. So these are the three that I've just built. I built them using emulation, but I could have built them on separate servers with the architecture that I'm targeting. So a hybrid build farm of different server architectures. From each of those servers, I push to Docker Hub, and then in the controlling job, I push the manifest list so that I get all these digests up here. And if you look, the digest, where's this one? So D395 is my Linux ARM64, and that is the Linux ARM64 tag. So the way this works is I push the individual images, then I push the manifest, and then the user, from the user point of view, they just pull latest, and they get whichever architecture they want. Okay, so let's go and see what we've got coming up. So close down my browser there. So yeah, as before, you can use the latest tag and you just pull this stuff down, and it'll be a match for whatever you're running. So the complexity is on the image publisher and the image builder. So if you want to support multiple architectures, the work is on you to make all this stuff happen. You're going to put it on your pipeline. It's all going to be automated. It's not going to be any kind of excessive hassle. From the user point of view, it just makes it super easy. So that's the end goal: making life easy for the users of your application or the readers of your book. And that means you take on more work yourself. But that's the price you pay. So in my case, I've got a whole bunch of machines that are all running Docker. I've got Jenkins running in a container, the same that we've seen in previous episodes. And I've got a job for pretty much every exercise and every chapter. I have an automated job to make sure that the images still build and all that sort of stuff. And they all these different machines that I've got, they're all the ARM ones are just cheap kind of boards. And then I've got a couple of little servers that do the Linux and the Windows stuff. And then they push it up to Docker Hub, and then the Jenkins build pushes the manifest. So same process I've been talking about. The alternative is much slicker, but it doesn't work in every scenario. So it doesn't work for Windows right now, although support is coming. The alternative is called Docker Buildex. So Buildex is like an additional, currently it's an alternative build engine for Docker that supports all the previous Dockerfile syntax. So I can use Docker Buildex instead of Docker Build, and use the same inputs and get an image in the output. But part of what Docker Buildex does, is it allows you to, firstly, it supports the emulation, so I can kind of do that in a single command to build for different platforms. But also it lets you build your build farm and manage it through your Docker Buildex command. So Buildex understands as a build farm. You give it a Docker file to build, and it will spin out to all those machines and build a variant on that. And it will push the images and create the manifest and push the manifest all in one go. It's not for every scenario because A, doesn't support Windows, and B, it doesn't support multiple Docker files. So in that scenario that I outlined earlier, where I have to have a different Docker file for each architecture so that I can use the right features inside my Dockerfile commands, it doesn't support that. It's single Docker file, multiple outputs. But if that fits what you're doing, it's a much nicer way to do this stuff. So if I go and scroll down here, I'm going to be using Play with Docker here again, because that's something that you can use yourselves to try this out, because it works better with multiple instances. So I'm going to go to playwithdocker.com. If you haven't seen this in previous episodes, online Docker Playground is free, like it's provided by Docker, the company. You log in with your Docker Hub ID, and you click Start, and you get a session where you can add a bunch of effectively virtual machines, which are actually running in containers, and they've all got Docker installed. So I'm going to add a couple of instances here. So I've got effectively two servers, both running Docker. And again, I can't really do much with the UI of Play with Docker. So I'm going to drag my chapter over to another monitor to clear myself some space. And I'm going to work from there. But all the commands I'm putting in, they're all in the chapter, so you can follow along this yourself. So the first thing I'm doing, I'm on node 1, so one of my fake servers, and I'm going to put in the IP address of node 2, because I'm going to use that as a remote context to be able to issue commands against the separate machine. So that's my IP address. I will SSH into that machine, into that fake node from this fake node. And I'll say, yes, I do want to authenticate that. Now I'm in node 2, so that's good. So the connectivity between those two is correct. If you saw the previous episode, which was all about remote access for Docker servers, the connection means that I can use SSH to do a Docker context. And that's what I'm going to do next. So I'm going to create my context, create two contexts. So on my node 1, I'm going to create a context which represents node 1 itself. So that's Docker pointing to the local Docker socket. So I've effectively got a copy of my default context, and I've only got that, so it makes it easier in my Buildex commands. And then I'm going to create another context for node 2. So my Docker context for node 2 is using SSH. So if you missed this was in probably episode 14. Seems like something I did yesterday, but then I think I did lots of things yesterday, so it might be an earlier one. This is about how you connect to a remote Docker engine in a secure way. I can use SSH here because I've got everything already set up in my Play with Docker session. It all just kind of sets everything up for you. So let's clear this down and check my contacts are all there. And I should have my two new contacts. There's a default one. Node 1 is using the local socket, and node 2 is using SSH to connect to my other node. Okay, so I've now got two contacts, and I can feed those into Docker Buildex. Buildex is context aware. So I'm going to scroll down to the next section of the episode here. What I'm going to do, oh yeah, so I need to show you this, because this is the first thing that I've seen when going through these exercises that doesn't work anymore. And it doesn't work because I've used an older version of Buildex. So I'm using 3.1, which all worked fine with the version of Docker that was on Play with Docker. When I did this, when I wrote these exercises 8 months ago or whatever, it's the first time I've noticed I need an addendum. So what I've got here is, if you go and look at chapter 16 in the README, there is an alternative command for this one, because the latest version of Buildex works and the version that I was using doesn't work anymore. So that's a lesson to me that I should be putting these commands in. Anything with a version number should go into a script inside the repo, so that I don't need to put an addendum in there. But that's what you need to do. So the exercise here, Buildex is an extension to the Docker command line. And the way that Docker does these extensions is they're just binaries that live in a particular file. So I'm downloading the Buildex plugin, which is from GitHub. So it's an open source part of the Docker project. So I've downloaded that. Let's get rid of this now, which you can't see. I've downloaded just the binary, and what I'm going to do is I'm going to move it into. I've downloaded it into the CLI plugins folder. So a binary that's in the CLI plugins folder, as long as it does what Docker expects, it gives me access to that new command. So if I clear this down, I can now do a Docker Buildex version, and that will show me it's 4.2. So it adds a new verb effectively to the Docker commands, or a new noun for me to do things. So I'm going to now do a Buildex create, and Buildex has this notion of different builders. So I've got a builder that I'm using. I'm calling it Chapter 16, and it supports Linux, AMD 64, and it's Node 1. So it's using the Docker context to find out what that builder actually is. And I've just called it CH16, and I'm specifying one particular platform that I want to use it for. I'm going to create another builder, and this is going to be appended to the CH16. So CH16 now has two build engines inside that builder. One for Intel 64-bit, one for Intel 386, so Intel 32-bit. The Node 1 is going to build the 64-bit images, and Node 2 is going to build the 32-bit images. So this is how I would do it if I was going to I had some ARM machines as well that I wanted to connect and bring into my build farm. I create a context for them, and I tell Docker Buildex to add them to the overall builder. So if I clear this down, and now I look at the builders I've got set up, so Docker Buildex list, and it's showing me I've got this. The CH16 is the name of the builder, and there are two endpoints in there, Node 1 and Node 2, and they're being used for 64-bit and 32-bit. If I look at the other nodes, if I wanted to build something individually, then these are I could switch to the specific node, which can do both. So each of those can do either 32 or 64-bit. But CH16 is able to do both at the same time. When I run a buildx command, it'll farm out onto both those engines. Okay, so it's super flexible. I'm going to skip down to the next part of the exercise. So inside here, I should put an alias in really. I'm going to clone the repo for the book. So I'm just going to download all the exercises here onto my Play with Docker session. When I quit this Play with Docker session, everything will have gone, so I don't need to worry about using up the storage or anything like that, or putting secret information in there. I probably shouldn't do that, but I'm going to do that in the next part of the exercise. So in my Docker ID here, I'm going to be Docker Buildex can take my Docker file. It can farm it out to all the build agents that are in that builder and build different architectures. And then at the end, push the whole lot up to Docker Hub together with the manifest. For that to work, obviously, I need to have it configured to authenticate with my registry. So I need to do my Docker login. So I'm putting that 6-side name into a variable, and I'm going to log in, and I'm going to make sure that my password manager is on the other screen. So that looks good. So let me just put this in here. If you go to Docker Hub, you can generate a token which you can use in place of a password if you need to share that for for an online service or anything like that. So it's your Docker ID, but it's a separate token that you can use to authenticate. And that's how you should do things like this. That's what I'm doing here. So I'm going to grab this token, paste that in there. Yeah, okay. And this is why you shouldn't do it, because it gets stored unencrypted. But we'll worry about that later. I clear this down. And now I'm going to use Docker Buildex build. So there's the Buildex command. It's kind of like the Docker build command, but it's going to work with a completely different engine. It's going to use that Buildex plugin instead. And what this does is it says, here's my build command. Here's the tag, which is folder list 2. These are the platforms I want you to build it on, and I want you to push it when you're done. Because I'm using, actually before I do that, let's go back to my Buildex list. And we'll see there are different builders available, but this is the one that's selected. So I could have different builders, and I could do a Docker Buildex use to point to a different builder. This is the one with the multiple build engines, so it's going to enable me to run that kind of multi-architecture build. Okay, so the output from Buildex is super cool. Everything runs inside containers, so it pulls this kind of build kit image, and then it goes and builds simultaneously. So you'll see that one of these is from node 0, one's from node 1, one's from node 2. They're both happening simultaneously. Some bits take a little while, so it creates the build engine, and that takes a little while to initialize. But that's all. That only happens the first time you use it, and then you see it's all like super fast load of output that comes out. And then the final thing is it's merged the manifest list, and that's it. That means it's built the images, the two variants, push them to Docker Hub, but it doesn't push the individual variants in the same way that I did when I did this manually. So let me roll back now to my chapter. And here, if I now go and look at my hub again and go back to my user account, so let's go to 6side. I should see now this folder list 2, which is what I called it. That should now be the latest one, and it is updated a few seconds ago. And if I scroll down, look at the tags, there you'll see there are different variants here. So there's 32-bit and the 64-bit Intel variants, but there are no other images. There are no separate images with different tags, which is what I had when I pushed my own multi-arc image. I've just got a single one, and Docker Buildex took care of all that for me. So it pushed up effectively the separate images and the manifest all in one go. So I don't have those separate tags in there. So when I do a pull, I can only pull based on the kind of umbrella tag, and I'll get whichever image is the right one for matching my architecture. So Buildex is really nice way to do it, provided that it supports all the scenarios that you need. Windows support is coming, and you see how far down the line we are with that. But again, when you have the Windows support, you're still going to have that limitation that you've only got one Dockerfile. So you need to make sure the Dockerfile instructions that you're using can work in all the platforms that you're trying to build on, because Buildex will just spin them all off. And if they fail, then some of them will just fail, and then the whole build will fail because it won't push a partially completed build. Okay, cool. So here's the thing about understanding. So this is kind of the wrap up, really. So understanding where multi-arc images fit. So the early feedback I got from submitting the chapter list for this book, one of the early reviewers said, I don't think we should have this chapter. And I was kind of, well, we are going to have this chapter because if nothing else, Windows support is important to me because that's my background. But also this little chart that shows you how this stuff works. So these are some of the official images. That's NAT, which is a message queue, Postgres, the database, the official Go images. They all launched on Linux only. So, 2014, 2015, as Docker was taking hold of the world, these teams published their applications to Docker images. And then eventually they kind of got to the point of, well, we're missing out a whole bunch of people here. So 2016, the NATS team and the Go team published Windows variants of their images. And then in 2017, when ARM started to really become viable to run like desktop applications in containers, then they all published ARM images. There's no Postgres image yet for Windows, which is why I've had to build my own for the examples in this book. But I dare say it will come. It's just dependent on the project team's appetite to support another thing. The ARM variants of Postgres are probably pretty simple because they're just Linux, so they probably got some small variations in the Docker files. Windows would be completely different for that team to manage, so that's why the reluctance there. But something you need to think about. Your roadmap might very well be Linux and Intel to start with, but if you're planning on a product that spans several years, one day a customer with a lot of money is going to ask you to support Windows, and you make the choice to say, yeah, we can do that. And to get that far, here's the kind of guidance here that you should follow. So all the golden images, all the official images on Docker Hub, they're all pretty much multi-arc. They don't all have Windows support, but that's something to check for each of those images. So either use those in the from lines in your Docker files, or create your own golden images from those official images. So The golden images for this book, all the DIAMOL images, don't use those because they're not production grade. They're just good enough to do all the examples and show you how all this stuff works. So don't take that as your golden images. Take the official images as your source of golden images, and then retag them and put whatever else you need in them. But if you want to see how I'm building all these things, they're all in the images folder of the source code. So if I have a look, I can show you some of these are easier to do than others. So way down here under images, so there's just a ton of examples of Docker files in here. So let me get Postgres as an example. So I've got two versions of Postgres. You'll see under the Linux folder, there's a single Docker file. So when I built, and that's it. This is my kind of golden image. I'm just taking the official image from Docker Hub, and there are Linux variants of this for Intel, ARM, and ARM64. So I just build them on the relevant machines and push them up with my tag, so that I know, I've got a good version using my tag. The Windows variant, totally different. So there's just tons of stuff in here because this the Windows download, again, this is an example that I've found elsewhere, and I've tweaked it to make sure it works for me. There is no official Windows image, so I've basically kind of custom built this so that it works in the same way. So it's still Postgres. When I run it in a Windows container, it behaves in the same way, but I've now got this to maintain. Whereas on the Linux variants, I've just got that to maintain. Another example, look at Node. Is Node a good example? Yeah, Node's a good example because there is an ARM64 and an Intel variant of the Linux image, but there isn't an ARM32 variant. So I've got a separate Docker file that uses a different base image for ARM32 support. And then for Windows, again, I've had to custom build this myself. So this is the position you get into. If you want multi-arc support, you bring on the onus of maintaining all this stuff, but it's super easy for your users. So I'm pretty confident that every exercise that you run, you shouldn't get any issues with, there is no image for that architecture because I've built all these and I have Jenkins jobs pushing them all the time. Okay, so let's go back to the chapter here. So to do that yourself, there are a few things that you need to kind of bear in mind. The main one is make sure that your base images are multi-arc. Make sure don't include any OS specific commands in your run or command instructions. If in your run instruction, remember that happens during the Docker build phase. So if there's something OS specific in there, it'll fail on a different operating system. So your build will fail, which is better than it failing at runtime, which is what will happen if there's something OS specific in your command or your entry point that relies on a utility like ping or whatever, which isn't in every operating system base. Then if you rely on that, then it might fail at runtime, which you definitely don't want. If you need some sort of complex logic in there, and I've talked about little utility apps before, write it into a little utility app because that will be multi-arc because it'll be the same platform that you're using for your actual application. So that's a good thing to do. And test these things. The thing that puts people off is you kind of need the hardware. So you can't just build a Windows variant. You need to be able to run the container as a bare minimum to make sure that it actually starts. And so you need Windows servers for that. With GitHub Actions, you can bring your own GitHub Actions runners. So you can have a GitHub action that does the Windows version because you can get Windows servers as part of your GitHub Actions builds. Just the Windows and Linux Intel versions, and you can use your own Raspberry Pis as GitHub agents so GitHub calls down to your machines to build the ARM variant. So you can do all this stuff. It's not super difficult to get there, but it takes a little bit more thought than just doing Docker build, Docker push. Okay, so if you've seen how this stuff works before, all the exercises in the chapter, you're meant to follow along with those if you've got the time, and to see how all this works and get the experience of doing this stuff for yourself and making sure you understand how the pieces fit together. Go and look at the relevant Docker files. Don't list every Docker file in the book because it would be 10,000 pages long. And each chapter ends with a lab, which is just sets you a goal and gives you a couple of hints for you to explore for yourself. Make sure you've kind of got all this stuff down. Make sure you understand the importance of how this works. And I don't go through those in the episodes because they're meant to be your own work. But there is a sample solution up on GitHub there. Okay, so we've got a question here on YouTube. So Docker Compose, can you define a default network? So that's not particularly to do with today, but yes, you can. So you can put inside your Docker Compose when you've got your network section. If you just name a network without saying that it's external, then Docker Compose will create it for you. And but you don't. That depends what you mean by default network. Because if I put something, let me try and find a Compose file, which might be easier said than done because there's just tons and tons of files in here. Let's go to chapter 15. Let's find a Docker Compose that has actually got something useful in it. Okay, so yeah, so inside here, I've got my network defined. I'm giving it a name, so like Docker Compose will create that for me. It's not the default network, as in the containers don't automatically plug into it. So you have to specify the network that you want your containers to plug into. So it can be a default, as in that Docker Compose will create it for you and manage it for you, so you don't have to explicitly do a Docker network create. But it's not the default for your containers. You have to explicitly plug them into the network, because containers can be plugged into multiple networks or zero. So in order for containers to talk to each other, they have to share a network. But I could have, a container that's on the front end and the back end networks, and it can talk to a cache container that's only plugged into the front end network, but it can also talk to a database container that's only plugged into the back end network. So yes, it depends what you mean by default in that case, but yeah, Docker Compose will manage them for you, but it's down to you to actually plug your containers into them. Okay, and that's about it. So I think that's it for today. So tomorrow, oh no, it's Friday, isn't it? So what that means is we've got the weekend off, and which is something that we should all be looking forward to. So let's switch back here, and here I am. So that's the end of this section. So week 3, all about container orchestration and the stuff behind that. So we talked about continuous deployment. We talked about securing access to your Docker engine so you can securely connect to them remotely. Today we've looked at multiple architecture, which is something that you should consider, especially if you're an application publisher, but also if you're spinning up and running your own applications. Think about ARM as a potential way to run your applications a lot more cheaply if you're up in the cloud. And then next week is part 4. Part 4 is all about, let me open it up because I've forgotten myself. Part 4 is all about preparing for production. So there's a whole bunch of stuff that I haven't really gone into a lot of detail with, which you need to before you get into production. So next week's the last set of episodes. There are again 5 episodes, one each day. And we're going to cover things like optimizing your Docker images, which I've mentioned several times, but we're going to deep dive into the techniques you need to use. We're going to look at configuration in more detail. We're going to look at logging, which is like super boring, but if you don't have it, then everything goes bad very quickly. And then the final 2 episodes are about some more kind of production grade patterns that are made so much easier with containers. So we're going to look at a reverse proxy, which is how you kind of manage traffic to your containers that comes in from the outside world. And we're going to look at message queuing, so asynchronous communication, which again is just made that much easier with Docker because it's so much easier to spin up these infrastructure containers and plug them into your applications. So yeah, so that was it for today. So thank you for watching. That was episode 15. We've got the weekend off, and I will see, if you're watching live, I will see you on Monday for episode 16. And if you're watching the recording, then episode 16 comes next. So thank you for watching. Hope you enjoyed it, and I will see you next time.